Thank you very much for having me today. I'm going to share some exciting results about retrieval of the lost literature from the Herculaneum Papyri with X-ray fluorescence microscopy. My name is Luxi Li. I'm a beamline scientist in Advanced Photon Source Argonne National Lab. In this presentation, I'm going to give a brief history of the Herculaneum Papyri and the fundamentals of the technique that we are going to use, the X-ray fluorescence microscopy. And then later on, I'm going to talk about some results from the Phantom, the test samples, to test the logistics of our hypothesis. And then we scan some real samples, the papyri fragments, to see, to read the letters inside the papyri fragments. So, is my voice continuous or is broken? Okay. So here's a simulation. Here's a simulation of the Mount Vesuvius eruption. So at that time, this pyroclastic flow buried a few Roman settlements in the neighborhood, in this vicinity, such as Pompeii and Herculaneum. And there is a private library that collected a huge amount of papyrus rolls near Herculaneum, was buried during the eruption. And this collection of papyrus stayed undisturbed until the middle of the 18th century when it was first discovered. And ever since, hundreds of papyrus rolls were unearthed from the site. And the conventional way to study these papyrus rolls is to physically open them and to read the content inside. However, this is a successful example of unrolling papyrus. However, for most of the case, it's impossible to avoid damaging them from physically unrolling. This is because the temperature of the pyroclastic flow can reach up to 300 degrees. So once the flow flooded this area, that immediately carbonized these papyrus rolls, made them extremely fragile. And since they're stored over almost 2,000 years, because of the pressure and the environmental fluctuation, these layers of papyrus can get stuck together, and with the pressures and the weight, they crumble, they deform completely. So it's impossible to unroll them. This is an example of a well-preserved Herculaneum papyrus. You can see it's a big chunk of black carbon type of roll, so it's impossible to open them. And so that's a lucky case, but most of the times we find them broken or damaged, and there are small fragments scattered around the site like these. So these are the samples we scanned for this research. So with the physically unrolling impossible, so scientists start to reach for the non-destructive method. And X-ray because X-ray has a strong penetration power, so that gives us the possibility to study these papyrus rolls in situ without unrolling them. And with advent of the third generation synchrotron, that gives us really high X-ray flux, that makes us easily to study with X-ray CT to resolve the 3D structure of the papyrus. But unfortunately, the absorption contrast between the carbon-based ink and the papyrus are so weak, so it's impossible to read the content inside. And then later on, my collaborator, Dr. Mochala, in the audience, so he and his collaborators used the X-ray phase contrast tomography, and they succeeded to read, to view partially the letters and some words in situ without unrolling these papyrus rolls. But this method is computational intensive. So later on, we thought about how about X-ray fluorescence, because this technique is very sensitive to trace element, so it can detect up to sub-ppm concentration. So what if we study the elemental distribution in the 3D fashion that is contained in the ink component? So this is what we think that might be possible. One way to retrieve the letters inside the papyrus. Here's the fundamental of X-ray fluorescence. So when the incident X-ray, if the energy is equal to or higher than the binding energy of the inner shell electron, it tends to ionize the inner shell electron, leaving a vacancy. So at this state, the atoms are very unstable. Therefore, the outer shell electrons turn to fall in this vacancy. In the meantime, it meets an X-ray photon. And the energy of this X-ray photon equals to the energy difference between these two electronic states. And this energy is characteristic to element species. Hence, if we can measure the energy of these characteristic X-ray emission as well as intensity, we're able to identify the element species and quantify them in the X-ray illumination volume. Here's a schematic of X-ray fluorescence microscope. Here's a picture of APS. A specific energy X-rays is selected by monochromator from synchrotron radiation. Then it's focused onto the sample. So the spot size of the X-ray defines the limit of the X-ray fluorescence images. Now we have a fluorescence detector located perpendicular to the sample. Usually it's an energy dispersive detector that detects a full spectrum from the sample illumination volume. Here's the detection logistics. So if the X-ray is fixed onto one point in the big sample, or if the X-ray is larger than the sample, so it's considered to be point detection. And this is the detector readout. It gives a full spectrum. So basically, by analyzing these peak positions in terms of energy and their integrated intensity, we're able to tell the element species and the concentration in this detection volume. And then if we raster scan the sample and then do the same analysis for every single pixels and then deconvolute them into element maps, here's an example of what we see, for example, chlorine, potassium, rubidium, and then overlap them for later data explanation. Then in terms of 3D mapping, there are two geometries. One is in the projection geometry. We call it X-ray fluorescence tomography. In terms of data collection, it's very similar. So we take 2D projective XRF images and then rotate the sample so that we get projections at multiple projection angles. And then we analyze the data and deconvolute into element maps. Later on, we sort these projections by element species and then run 3D reconstruction with normal tomography algorithm. Since X-ray fluorescence microscopy is a scanning probe, the data collection is very time-consuming, and also there's self-absorption issues with this technique. However, with, for example, the ESRF upgrade and later the APSU, the X-ray intensity will be increased dramatically, so that will reduce the total data acquisition time dramatically. So that's one of the advantages of the upgrade of the current synchrotron radiation facilities. And there's another geometry. So this is a top view of the instrument. So all of the setup is very similar, except for we put a focusing optics in front of the detector. So that allows us only detect fluorescent signal from a specific depth in the sample. So this way, we just go to different, so by adjusting the detector to sample distance, we're able to detect slices in the sample in depth. However, because it only detects a few percentage of the total X-ray fluorescence signal, so the signal level is really low. It requires much higher X-ray beam. Again, this technique will definitely benefit from the upgrade in the synchrotron radiation source. All right, so once we go through the schematic of the technique, first thing we do is to scan some synthetic sample to test the feasibility of this work. So we are proposing, by studying the 3D distribution of lead, we're able to identify the letters underneath the top layer. So this is a modern papyrus. So we laid 3 layers. Each of them has letters that are written in lead-rich ink. So we stack them together and then scan it with confocal XRF mode. So this is a 3D reconstruction of the lead signal. You can see, we can clearly identify the letters throughout the 3 layers. And they are not exactly flat, but we can clearly recover the letters from the top layer all the way to the last. Once we got the proof of concept, then we scan some real sample. So this is a small papyrus fragment, about 1 centimeter in diameter, but the thickness is very, very thin, about 200 microns. So that may consist of a couple of layers of papyrus. And we can see, even from the visible light microscope, you can see there's an O-shaped letter on the surface. So that's our first attempt. Hopefully, we can see the zinc distribution that agree with the letter. So here's an integrated spectrum of a 2D scan from this sample. So we add up all the signals over all the pixels. That gives us good signal-to-noise ratio. So we can see here the common elements that from papyrus. It may vary from the source. And then here are the possible elements that come from ink. We have lead, mercury, iron, copper, sulfur, phosphate. And from the integrated spectrum, we can see most of the elements. And if we focus on lead L line and lead M line, we can see there's a significant amount of lead inside the sample. So, however, if we go to 2D distribution, these are the element maps of these commonly seen elements. And we overlap calcium, which is rich in papyrus itself, and then iron and lead. We pretty much see lead overlap with the other 2 elements, which means lead distribute evenly inside the sample. So that leaves us with the question, where does the lead come from? So this may come from the water during the manufacture of the papyri. And then we tried a different sample with a much thicker size. It is about 2 millimeter in thickness. So there are 2 letters that are quite visible from the surface. And then we did slightly different approach. So we scanned it in the projection fluorescence geometry. And over this area that is supposed to have letters, lead signal doesn't show up anything. However, there's this spot that lights up. It seems it has a huge amount of lead in this area. So we zoom in to see this area, and then we see a Y-shaped letter. And also the size is about 2 millimeter by 4 millimeter, which roughly agrees to the size of the characters. And then, so we run a fluorescence tomography scan, and this is the lead reconstruction that we got from the data. And then you can see this character is quite deformed. So this is this might come from the long time storage under its current condition. All right. I want to thank my collaborators, and all this experiment were done in APS. Thank you very much. I'm glad to take questions, and then if later on, if you want to discuss with me, feel free to email me. Thank you very much.
Thank you. So we have time for one or maybe two questions.
Maybe one comment about lead. I think we are going to find it more and more in ink. I mean, it seems that your collection, we found it. In Herculaneum, we found it. In there is another poster from a collection from Copenhagen where we've also found it. And I think this is really not a contamination, but it's really an ingredient which is part of the formulation. And what we are working on now, as you found lead as lead soaps, and we also found them as lead soaps. So more and more, I mean, at least but maybe more people have the idea that lead was used really for the formulation of ink, possibly for maybe a dryer, possibly of the binder. So my guess is that more than a contamination, it is really something which was used on purpose to modify the properties of ink. But, well, we will see.
Yeah.
On this point of view, what I know is that on this point of view, one fragment of the Herculaneum Papyri was identified with lead as ink. I think is one in the Louvre collection. I did some analysis on other Herculaneum Papyri, which are in the Museum of Naples, and I found lead everywhere in the papyrus.
Yeah,
so
like what I show over there, yeah, it's evenly distributed throughout the sample.
And we were thinking about some contamination by the environment,
so you mean
after this is an hypothesis anyway.
You detected lead in
everywhere.
the papyrus, independently of ink.
Yeah, everywhere,
okay.
Everywhere.
Yeah.
But it can also be. I mean, we can also envisage that then it was a papyrus which was prepared in some way.
It's possible.
Yeah, these are
to prepare the surface for writing with something which contains that.
Maybe Olivier knows better because he also made a lot of measurement in library in Naples. Finally, we found, correct me, in all, at least all the Greek papyri, because there are 10% that are Latin. There were metal in all the Greek, sometimes iron, sometimes, but up to us, Marine should remember, the amount we found of lead is pretty high, cannot be contamination because it's very, very high. What we found in one single fragment is extremely high. So, but sure there is lead in water. So
yeah, you can see the lead signal is quite strong, and it's for this case it's evenly distributed.
So there is lead in papyrus somehow, but the amount we found in measurement in years ago
exactly, but
it's too high. It's too high. Too. I didn't remember now, but extremely high. In one fragment, the correlation of the amount of lead was incompatible with the contamination, honestly. But
it shouldn't be surprising if lead white was used to brighten the writing surface, and in later times, Islamic manuscripts are often burnished with lead white, just in the way that vellum might be burnished with chalk to make a whiter, more dense surface, and also to control the way the ink flows on the surface. I once had to transport a copy of the Quran back to Turkey through airport security, and it was absolutely opaque in the X-ray machine. Because of that, it was a big problem.
And this reminds me that, always on this question about lead phosphates, where is it coming from? And we have the only text so far that we have where we have a mixture of lead white and bone white, which could be the starting step, is so far from Cennini, which is explaining how to coat parchments for drawings or writing. So it may be something, an explanation for the presence of lead as well, like preparing the surface for a later use of the papyrus. Yeah.
It looks to me we have all the possibilities from
All possible explanations.
lead everywhere, from almost no contrast, a bit of lead, but
Yeah.
almost no contrast. So, yeah, probably it needs to
Probably,
depends on the
yeah.
time.
Well, there is contrast sometimes.
Sometimes.
Yeah, like this one. It's quite obvious, right? You see this letter stand out in lead map in comparison to other ones, other elements. I want to make a comment to the previous talks that I remember the audience asked about. Is it possible that this ink contains lead phosphate?
Phosphates, yeah.
Phosphate. So I mean, in this case, because I don't see anything in the sulfur except for it looks like it's a surface structure. But again, with extrafluorescence tomography, we have the self-absorption issue. So like the fluorescence energy with sulfur is 2.3 keV. So if the sample is thick enough, the signal may not be able to penetrate through the sample and just get absorbed on the way propagating to the detector. So this way, it's really hard to tell if there's a sulfur counterpart respectively to lead inside the sample.
Yeah, it's important. Indeed.
So, right, because over here we see pretty much the signal from the more towards the surface.
Yeah, indeed. We detected it a couple of times because we were under vacuum at ID21, so we had the possibility we had a very good sensitivity to phosphorus, and also because the samples that we measured, the ink was on the surface, but in your case it may be a bit challenging indeed to probe the signal, and let's say to give link phosphorus to an ink which would be internal to the...
Right, it might be difficult to tell if it's lead carbonate or phosphate or sulfate. But this way, at least we can use the zinc, the lead signal to read the letter.
Then we should go to diffraction.
Because the energy is high, so it has a much stronger penetration power.